Alright, so for section 5.5, we want to look at some applications and how to use logs that don't have base E. Alright, so just as a reminder, the natural log of x is the same thing as saying the log base E of x, right? So we want to use things that maybe don't exactly have a natural log component. And so, as an example, let's say that we wanted to look at something like, let's say the log of base 4 of 16. Okay, so what my goal of this is to figure out what power of 4 would result in 16. Okay, and so the log of base 4 of 16 is just what power, so what value of x do I need to have 4 to the x be 16? I can plug that in the calculator, but this one's kind of easy to see that it's just 4 squared. Okay, so that's the kinds of questions that we're going to look at that have to do with logs that don't have base E. And these applications are things like Half-Life, some finance situations that these are usable for. But we'll just look at a few different examples on how we can use this. Okay. So the first things that we want to know here are the derivatives. So let's look at derivatives for these. So let's say that we have some number a that's being raised to an x power. All right, so the derivative of that is the natural log of a times a to the x. Okay. In a similar situation, if we have something that's other than just plain old x, so we'll say u, then that is the natural log of a times a to the u, and then I have to do the chain rule. Okay. All right, so let's look at an example of that. Let's say that we have, we want to find the derivative of 7 to the 8x. Okay. Well, my rules here say that I'm going to have 7 as my a because that's the base. So I have the natural log of 7 times 7 to the 8x, and then I do the chain rule, so I bring that 8 down. Okay, so then I would have times 8. All right, so if I wanted to clean this up a little bit, I could say this is 8 times the natural log of 7 times 7 to the 8x. Okay, so that's an example of how that derivative rule gets used. Okay, this is not one of those derivative rules that I anticipate you just to remember. It's something to reference just because of how similar they all look and different things. So this is not something that I think you should just have memorized. All right. And so let's look at another derivative here. Let's say that we are given something like log base a of x. Okay, the derivative of that is 1 over the natural log of a times x. Okay. And then on a similar note, if it were anything other than just plain old x, so maybe it's some kind of function. So we have log base a of u. Then that is equal to 1 over the natural log of a u times du dx. Okay. And we can look at an example of that. Let's put this one into use. Let's say that we want to find, let's say we have y is equal to the natural log of, we'll say base 4 of x squared minus 5x. Okay. So again, just referencing, my rule says that I have 1 over the natural log of a times u times the derivative of the u portion, so the chain rule again. Okay. So to differentiate this, I'm going to say y prime is equal to, so I'm going to have 1 over the natural log of my a, which is 4, so the natural log of 4. Okay, so just I have 1 over the natural log of 4 times u, so u is x squared minus 5x. Okay. But then I have to also do the chain rule part, so I have to take the derivative of the inside function, which is 2x minus 5. Okay. Now I can clean this up and I can say, well, this is 2x minus 5 all divided by, let's say, okay, so I can factor out an x out of my original u because I have x squared minus 5x. So I'll say that is x times x minus 5 times the natural log of 4. Okay. So again, it's just about knowing these log rules with derivatives and how they work when we don't have a base e situation, so a natural log. All right, so there's an example of that and how that works. All right, so now let's look at this from an integration standpoint and say, you know, if we want to take the integral of some number a to the x, you know, what would that look like? Okay, so that would look like this. We would have 1 over the natural log of a times the original function a to the x, and then of course our plus c. All right, so let's say that we have a number like 7, so we're going to do 7 to the x dx. All right, so the integral of that would look like 1 over the natural log, my base is 7, okay, times the original function 7 to the x plus c. Okay, so just to clean that up, we can say that's 7 to the x over the natural log of 7 plus c. Okay, so that's how this would look as an integration standpoint when a is just a real number, so it's not any kind of log aspect, but this is what it would look like. Okay. And so then the last thing that we want to be able to do with this, and kind of the whole purpose, is some compounding interest or anything that grows or decays exponentially, and to be able to find rates of change, because a derivative is really just a rate of change. Okay, so here are our two most common compounding formulas, and this is kind of from a finance standpoint, so we'll say compounding interest. All right. When we are, so compounding just means how many times that interest is calculated, or how the period's interest is calculated in, and we always have a present value times 1 plus an r over n times n to the t. All right. R is the rate, so the interest rate. N is the number of compounds. And T is time. Okay, T is normally in years for these kinds of problems. And P is our present value or present cost. Okay, so whatever our initial value, what we're starting with, is P. All right. And so let's look at an example. Let's say that we have, we'll say the problem on your homework is the cost of oil changes. So we'll just go with that. Okay, or one of the problems on your homework. All right. And so the cost of oil changes can be represented by the present cost times 1.03 T. Okay, so I could tell you what if I know a present cost of oil changes, and then I could tell you for any year what the oil change would be, what it would cost in that year. Okay, so let's say that we have, we'll say that right now in 2025, we'll say that oil change is $23. Okay, and I want to figure out what is the cost of an oil change in, we'll say 2030. Okay. So then I would want to know when T is equal to 5, what that is. So we'll say that C of 5 is equal to 23 times 1.03 to the 5th power. Okay. Plug that in the calculator, and I get that the cost of oil changes in 2030 is $26.67. Okay. Well, that's all great and dandy, right? But now, from a calculus standpoint, because this is this is more of a financial math type question. So what we want to be able to do is to be able to answer questions like finding the rate of change. So let's say we want to find the rate of change, because we can't just calculate a slope using traditional slope methods. So let's find the rate of change when T is equal to 1. So in 2026, how much is it changing in 2026? All right. So we have something like, we have our function, we'll say our cost, so d dt of our cost function, C of t. Let me just erase this and start over. Well, of course my eraser quit working, but that's okay, whatever. All right, so there it goes, of course. So we're going to find our cost function, or the derivative of our cost function. So we're going to find the derivative of this. It doesn't matter what P is, because that's not going to change how fast or slow it is growing. So we'll just kind of ignore it for just a moment. All right. And so just as a reminder, the derivative of something, number to the x power, is just the natural log of that number times the number to the x power. Okay. So my derivative here, I'm going to just bring that p over because it's just kind of tagging along. Okay. So my derivative is the natural log of 1.03 times 1.03 to the t power. Okay, so that is my derivative of my function, which will tell me my rate of change. Okay, so now if I want to figure out what the rate of change is when t is equal to 1, then I just have to plug in 1 into my rate of change function, or my derivative. Okay, plug this in the calculator, and you'll get that, and it asks you to round to 3 decimal places, so we'll do this, P. Okay, so your homework asks for 3 decimal places. All right, so that concludes section 5.5. As always, if you do have any questions, please feel free to email me, and have a great rest of your day.